Hello everyone, thank you for joining this webinar session. Today's session will be conducted by three of my colleagues, Mr. Vijay Kulkarni from our US office, and Karthik and Bhavya from our Indian office. Over to you, Vijay.
Okay, thank you and welcome everybody. I appreciate you joining our webinar on 5G. It's a very exciting technology and holds a lot of promise for yet another revolution in this telecom space that we've all been witnessing for the past 20 years. Just incredible. Okay, so GL is very proud to be in that telecom industry, and we are located in Gaithersburg, Maryland since 1986, and we've been hard at it at developing products for the telecom test and measurement industry. We also do consulting in that same space. And through the years, we've developed all of these technologies that are so fascinating, starting from plain old telephone service to this revolution in wireless and IP and previous to that, SONET, SDH, all of these networks. Just a tremendous amount of change and also change that produced in the society as well as a result. So one of the things that we specialize in is analysis, monitoring, this visualization, of course, the emulation of all these different protocols. Telecom networks are, of course, the backbone of telecom networks are protocols. The methods by which we establish connections, sessions, data, voice, video sessions, so on. All of these are driven by exact protocols. And we have implemented an architecture for modeling, for actually emulating these protocols. And we have a couple of very smart architects that have done that. And Karthik is one of them, and Bhavya is the senior systems engineer. And you'll also be talking to Rob Bishevsky, who is also one of our great architects for providing this architecture for modeling all of these protocols and being able to help the industry implement this. So this is what we've been doing for the past, 30, 35 years. We're proud of some of the equipment that we've produced. So today, we're going to be focusing on 5G. And so we'll talk a little bit about the standards, the requirements and use cases. As you know, 5G has extremely bold statements about what they want to accomplish, and a lot of it is already, taking shape, which is really fantastic. And there's a lot of, because of the challenges or the requirements that you'll see in just a moment. There's a lot of testing challenges. How do you test things that are happening at such high speeds, low latency, such high throughput, and with so many connections? You all know that in 4G, one of the big things about 4G was always on, right? Always connected to the network. That was a great thing about 4G. And now we've added all of these other machines that are going to be part of 5G, and they always have to be connected. So there's lots of testing challenges. So today we're going to talk about the core, 5G core. So as you remember, the 4G had a evolved packet core, right? I think it was called EPC. And 5G similarly has a 5G core called, and our guys have implemented this 5G core, all of the protocols within it, and allows you to emulate a real 5G network. In fact, we have a real 5G network in our lab to demonstrate these protocols. And around the way we do it, we use this architecture called MAPS, Message Automation Protocol Simulation. And we'll talk a little bit about that. That allows us to emulate simple two-wire analog telephone calls, POTS, all the way up to 5G. voice over new radio calls. So we'll show you actually a call being established between two 5G phones in the new radio architecture. Okay, so here are the 5G performance requirements that one of our guys put together. And they're very, as you can see, they're extremely bold requirements that the industry is trying to meet. Peak data rates of 20 gigabits downlink, 10 gigabits uplink. That's generally probably it's possible with the millimeter wave antenna MIMO technology. Very low latency for applications that demand that. Certainly voice doesn't demand it, but certainly some of the applications that they've been talking about where you have edge computing and for automated cars connected all the time, they would need to know what is the location of all of these things at an instant. So those types of applications, especially things like virtual reality applications, or if you're doing remote surgery. In fact, that's actually, I've seen a demonstration of that. So those require very low latency. Bandwidth, of course, per unit area, they're saying 1,000 times the bandwidth. So 4G took it to one level, and here, if the coverage area is able to, have the millimeter wave propagation radio coverage, you can achieve that type of bandwidth per unit area. So one of the things that even 4G, advanced 4G, I guess, introduced was this Internet of Things, where you started connecting lots and lots of machines, millions of them, and now they're talking about billions. So that has even gone one step further with 5G, I think, with this type of connection density. Literally, we want to have all machines connected to each other, talking to each other. Some people are worried about that, actually, and what that foretells. Guys like Elon Musk, he thinks artificial intelligence might pose a big problem. Well, another thing is, because of those IoT Internet of Things, they're low power devices. So you want to be able to have very long battery life. And I'm going to quickly go through these now. They want to also have a reduction in network usage. This is all as a result of better battery technology and also the type of propagation that you have and the closer in network topologies that are there that all produce a reduction in the network energy. So you don't need as much broadband energy as you did in the earlier networks. And very high reliability, especially for some of those applications. And in some applications, of course, you want 100% coverage, especially for those edge computing applications where you want everything connected and everything talking to each other. So these are the bold requirements, and I think these are all evolving, or they have their evolutionary paths through the standards process. Here is the 3GPP standards that are release 15 has been released. Enhanced broadband. This is being implemented in a lot of countries. Some countries are far ahead on this. Release 16 and 17 are going to bring those other capabilities to the fore. I think a lot of this is expected to happen by 2025. So that's really amazing. All right, so now let's go to this. There's another way of looking at it. Those same three features or functions that 5G is meant to handle can be shown this way, in this sort of triangular fashion. Enhanced broadband. This is one of the main principles, foundations of 5G, which is just high throughput. Okay, very, very high throughput. Of course, that will support legacy voice and video, right? But more important, 5G is all about data, at least the latter parts of 5G, and that's going to be useful there. The other foundation of 5G is this massive machine type communications where you have lots and lots of machines connected, smart homes. So you can see all of these things. And then over on the other edge is the ultra reliable low latency communications, where you can really have incredible computing, and we'll have to see what happens with self-driving cars. I understand that, you know, in Las Vegas, already we have Tesla is introduced self-driving cars in Las Vegas from one of those gambling places to the other. It's all automated. I think they're putting that into motion here shortly. Okay, so that's sort of the big picture on 5G. Lots of applications, lots of services. Some of them really challenging, and so you need an architecture to be able to test all of this, and that's what we're going to be talking about. This is just another way of saying the same thing that we were just talking about, except that now we're using terms like network slicing, because those three big broad applications that we were talking about require at the edge different types of capabilities, and also you need different types of software within the core to be able to provide all of that functionality, and that's what this is talking about. So we'll talk about this a little bit, and I want to turn it over. Well, after this slide, you can see here the worldwide deployments. Some people are ahead of others, but I have a 5G phone, so I've noticed better throughput on my phone. So it's actually happening. So it's not just a wishful thinking. So it's actually happening. Lots of 5G phones are out there. So we'll get right into it now, okay? So Karthik, can you talk to us about what we have to offer and what the architecture looks like? Go right ahead.
Yes, Vijay, thank you. Hi, everyone. Okay, so I'll be briefly talking about the 4G to 5G evaluation and the network node and the protocol used, and how GL provides a testing tool to test these protocols and network elements. Okay, so there are two important architectural changes has happened when moving from 4G to 5G. Okay, one is the control user separation, user plane separation, and the reorganizing the network functions as services. Okay, so here we show the 4G. From here we'll see how the 5G has evolved, and what are the 4G functionalities or 5G functionalities being mapped to the 4G network element. Yeah, so control and user plane separation is called CUPS. Okay, so it is wise to separate these two so that both the user plane and the control plane can evolve independently. Okay, it is essential because it allows the operator to optimize the network where they can put the control plane functionality at the centralized location, probably like middle of the country, but the user plane, those gateway functionality can be pushed towards the edge. Okay. So and also both control plane and user plane will have a different kind of scaling. For example, enhanced mobile broadband will have more number of data plane activity, user plane activity than the control plane activity. But in term and otherwise, like probably the IoT kind of applications where you have many of the control plane activities comes into play. So it supports increasing the data traffic by enabling keep on adding the user plane as the data, the speed requirements and the number of subscriber increases. Okay, and you could easily locate and scale the control plane and user plane independently based on the demand. Okay, so it also brings the software-defined networking where the control plane can control multiple user plane and set a set of rules.
Okay, so one thing you said, Karthik, that was kind of enlightening to me anyway, was the fact that when you do this separation between control and user plane, you said that the controls can all be converged to one location centrally. And that's where this concept of cloud that they keep talking about is very relevant, right? You can put all of this control within the cloud at one location, and the edge could be mostly hardware. Am I right about that?
Yeah, you're correct.
Okay, that's great. That's why you hear a lot about cloud when you're talking about 5G. They talk about network function virtualization and cloud. What Karthik just said about the separation of control and user plane and data plane is what is at the heart of that. Okay, thank you. Keep going.
Okay, so there are the basic principles where the control plane functions can interface with multiple user plane functions. So this can be based on a particular requirement. So each user plane functions can have a different services or different advantages it has. So control plane has a ability to choose the user plane. Usually the one UE will be served by only one control plane, but there are like many user plane can be used based on the PDN connections. Control plane function controls the processing of packet. So it is going to provision the rules in the user plane which sets a set of packet forwarding rules. And in turn, the user plane apply this rule and report back all the usage and other quality of metrics it calculates.
So one thing that happened, Karthik, is when we did this separation, a lot of the protocols were drastically changed from 3G, 4G into 5G. Am I right there?
No, from 4G to 5G, it has been changed.
Yes.
Actually, yeah. So this actually standardized. Even before that, the individual implementation, they would have some kind of these two functions or the services are separated, but they would be communicating using a proprietary exchange of protocol. But now it has been standardized so that you can have a control plane from one vendor and the user plane can be bought by the other vendor. So usually those are the cheaper white box switches or gateways. So that is what it allows. So this is evolved. The release 8 was the old method of doing it, where the serving gateway and feeding gateway had both control and user plane functionality. So then in CUPS release 14, they have separated between the control and user plane, which had serving gateway and the PDN gateway. And in 5G combined, this one, both serving gateway and the PDN gateway functionalities are merged together and is a single node now. That is called the UPF, user plane function. Okay, the other major thing happened was the service-based interface. Okay, where it borrows that protocol or the method from the web services. Okay, in web services, actually the service provider actually develop a service and deploy and publish that information into the service registry. And whoever service consumer, they contact the service registry to discover the service and their own locations like IP address and other things. And then they contact the service provider to consume the services. So in 5G also, most of the services now or the network functions are implemented as a services. And there are mechanisms to register those services and discover those services independently so that you don't need to configure each and every network element about other network element. So that particular functionality is provided by NR, network repository. So you can consider it as a dynamic DNS where you just know the URL and you'll know how to reach the services. Here the mapping of 4G and 5G network element. So here the main part is MME functionality has been divided into access and mobility management, AMF, and the session management. Okay, so in MME handles both the session management and mobility management. Now it has been separated. Okay, now the AMF handles the UE registration and mobility management, and the SMS handles the PDU session management. And the AUSF handles the UE authentication part. Previously, it was done by the SSS. Though it gets the information from HSS, the calculation part is done at the AUSF side. And on the gateway side, the PDN, that one, it has been separated into SMF and UPF. SMS handles the control plane functions like UE/IP address assignment and UPF selections. And UPF handles the packet routing, quality of service enforcement, and charging functionality. So it reports the data usage back to SMF. Okay, so there are new 5G network functions, which are the slicing function, network exposure function, and network repository function. Okay, so those are the new functions. All others are can be directly mapped to this one. PCRF, now it's called PCF, which takes the same policy and control functions, and UDM takes the HSS role. Okay, and application function remains same as it is. This is it's a kind of service-based architecture. So here this is a service-based endpoints. Okay, actually they host the services performed by them. All other network functions access these services by using HTTP REST APIs. Okay, so for example, UDM hosts services like subscriber data management, which can be accessed by either AMF or SMF.
Okay. So these elements here, they access this database or registry information using REST APIs as if they were web-based services, right?
Yes, correct.
Mm-hmm. So everything has gone to REST APIs or web-based architecture. Okay, yeah, cool.
Exactly. Yeah, it's another way of representing, but that is the reference point representation, similar to what we use so far until 4G. So only 5G introduces the service-based architecture. So let's go over quickly about the functionality. So because once we know that, we'll know how to test that those network element. AMF includes, so actually it terminates the RAN control plane. It does the NAS ciphering and integrity protection. It handles the registration, connection, and mobility management, and also participate in lawful interception, and all the authentication, authorization, and security context management is done by the AMF. So session management functionality of the 4G has been moved to the SMF, as I told you earlier. Okay, so it includes the functionality like session management, IP address allocation, and it also selects the UPF, appropriate UPF for a particular functionalities. And also it applies the policy and quality of service in UPF. And also it participates in the roaming functionality. And AUSF, it provides the authentication functionalities. The other infantile element is the NEF. Okay, so it actually provides a means to collect, store, and securely expose these network functionalities to the third-party applications. Okay, so this is a new concept in 5G, where before there is no way that the third party can come to know what is happening within the network. So now 5G allows third-party application, if allowed by the network provider, they know what is happening within the network overall. Also, they can also get the services per mobile subscriber. Okay, one use case we can just take a look at is, for example, operator A trying to provide is trying to troubleshoot a subscriber who is actually now roaming in the operator B. Operator has no access to operator B, so he can just register for this exposure function, which can track the particular mobile. So is any problem with the operator B, the operator A will know, and then take the appropriate action on it. So, and apart from this, there are many application functions which can work well if they know what is happening with respect to mobile within the network. So that has an advantage. And the NRF, as I told earlier, okay, so it actually maintains the repository of all the 5G network element. Any 5G network functions comes up, it registers with the NRF. So the other network functions which are searching for this particular functionality, they can just contact the NRF and they get the details about the like IP address and other information, so that they can contact the appropriate. So you don't need to manually configure the other network functions IP address or the URL.
So all these boxes where we have GL maps, that means that these, before we showed you all these network elements, we have implemented the actual script-based protocols that are, the actual protocols that are defined, so that you could actually test each and every one of these. We'll get into that a little bit later.
Okay, so here are the protocols which we would be dealing with, mostly on the core network. A brief look at this protocol is like RRC is like it includes the connection establishment or the radio interface, release establishment release functions, and it does the system information broadcasting and bearer establishment, and also it provides a paging notification. And PDCP, it involves like ciphering and deciphering and integrity protection. NGAP, it is between the AMF and GNB. So it includes initial configuration exchanges between the AMF and GNB. It has a PDU session resource management. Okay, and also carries the NAS protocol messages between AMF and GNB. Okay, PFCP protocol, so it is used between the SMF and UPF, okay, which actually it is a protocol used for the cups, okay, to include set of rules and assign IP address and the do assign the GTP ID, things like that. Okay, so and the core network user plane has not changed much. So it continued to use the GTPU. Okay, on the air interface, the new protocol has been included, that is Service Data Adaptation Protocol. This is mainly for handling quality of service at the air interface. So what does this? It actually marks the packets with the correct quality of service flow ID. So that allows that particular packets being forwarded throughout the 5G core. So it ensures the quality of service as it travels through the 5G core.
So for example, packets that require very low latency would be tagged, and the core network would provide a different quality of service for those packets.
Exactly.
Mm-hmm.
Okay, so now we have so what our test solution is trying to test all the nodes which we have seen so far, and also we are dealing with all the protocols which we have explained so far on the 5G core network. Okay, so the major challenge the equipment manufacturers and service providers what they are facing is constantly changing the specifications as it is maturing now. Okay, so it is important to do a detailed protocol validation as the new releases are being released by 3GPP. And the other challenge comes from the service-based architecture that is different from what we have seen in the previous protocols up to 5G. And also we need to have the end-to-end testing once these protocols have been tested individually. So if all the element puts together, whether it works, so it provides a proper data and voice quality. Okay, those are the things have to be tested. So this requires some of the generic requirements like a test automation. And so during initial stages of the development, you need to impair and do the negative testing with respect to protocol as well as the traffic. And you need a test tool for all phases of the development, from design, development, deployment, and post deployment, where you may have to recreate the live network scenario in the lab. So you need a test tool which is able to recreate those scenarios at will. Okay, so it's also should be able to do the functionality testing and also, if required, the high density load testing.
Well, you just described what our capabilities are with our message automation protocol simulation architecture, what's capable, what we have implemented, so that for 5G we can do these types of regression testing, automation testing, protocol validation, impairment, and including functional and load testing, right? So
yes,
this is what our MAPS product for all of those protocols that were highlighted we can do. Okay.
Our testing solution starts from testing a network element in an isolator. So we would be able to test the network element, isolate that, and provide all other functionalities which it interacts. Okay, GL will emulate that to test the all the functional of that particular element. That is the first step. Then you put together those elements to create a 5G core or IMS core. And then finally you integrate both the entire 5G core and IMS and do the end-to-end testing, both in terms of real mobile and the test applications, or emulated mobiles where the GNB simulates n number of thousands of mobiles which loads the network. Okay, so here we are talking about the IMS isolation. And so these are the functionality which we would be testing. Okay, so it actually AMF terminates the N1 N2, and we'll be testing about its ciphering and integrity protection algorithms. Other test cases are registration, connection, and mobility management, and whether it's able to authenticate and authorize the services. And also AMF, whether it provides a proper transport towards SMF, whether it transparently carry the session message, session management messages to the SMF, and SMS messages to the SMSF, and whether it's provide the location service management for regularity services. And also its ability to do the notification when the network exposure function registered for the notification. As the network, the mobile registers and deregisters, it should trigger a message to the network exposure function. So similarly, SMF, okay, we will be testing, we will be simulating the AMF, UDM, and UPF. To check the SMF features. Okay, so its ability to do the session management and the IP allocation and deallocation and the registers, and its selection of the user plane based on the different quality of service and different DNN network configuration, and whether it's able to register or enforce the quality of service thing to the UPF, which it receives from the PCF, and its ability to calculate the charging data based on the report submitted by the UPF, and also whether it's able to discover the PCSF IP address of the IMS network. Okay, so this is the important aspect where the UPF isolation testing, where you will be actually testing the user plane. Okay, so this is the only node in the core network which deals with the user plane. Okay, so some of the functionalities, whenever some of the user plane functions allocate the IP address prefixes, and also its ability to routing and forwarding, both in some features and ability to apply the quality of service based on the flow identity. So its ability to understand and enforce the quality of service defined by SMF, and also whether it actually submit the usage report periodically to the SMF, which will in turn be used for the charging. So here what we do is we will be interfacing with the N4 interface which does the control plane. Once as the control plane happens, we will be generating a traffic at using packet load, which is a high density TCP UDP packet generator. So it will generate on the particular the flow ID and GTP tunnels. Okay, that the forward capability will be analyzed and reported by the other packet load which is there on the N6 interface. Yeah, so UDM is an important aspect. Most of the network element interacts with this. So it actually it has a lot of subscription information, which is very useful in AMF and SMF deciding the call behavior. Okay, so the AMF first, during registration, it downloads all the subscription detail from the UDF. So it is important to test the UDM. So UDM provides this authentication credentials which are configured there. So it also identifies the user based on like a private key, and it gives all the subscription management to the AMF and SMF. And also it is very useful when the SMS is going to be delivered on the MT. So it's going to identify where the mobile is present in which particular cell. So UDM provides the detail so that paging can be done to that mobile and the SMS can be delivered. And also it provides the authorization based on the subscription data which are configured within the UDM. So these services can be tested by having other network elements surrounding it and pumping various protocols transactions to verify its behavior. Okay, so though the importance of SMS nowadays coming down, but this is a very basic requirement of any cellular network. Okay, so still it becomes this is a basic one, though the usage has come down. So this is going to verify whether the SMF is ability to store and forward the SMS messages to the mobile to the one mobile to the other. So it is being wrapped. It can be tested by having AMF and the UDM. So you can simulate SMS between the mobiles. Where the SMF will contact the UDM to get the mobile location and again forward back to the corresponding AMF. And also its ability to generate the CDR for SMS also can be verified. Okay, so this is a new addition to our product where NEF Isolation, NEF testing, where NEF can register different, it can subscribe to various notifications, various events in AMF, UDM, and SMF. So when those particular event happens, this network element will be send back the notification based on the subscription details, subscription configuration. So which can NEF can then expose the same thing to the application functions. So it also used to set the packet flow description, which will change the quality of service. Okay, so once the individual elements have been tested for the individual functionality, then you can put the entire 5G core network into a test where the GL can simulate GNB with thousands of subscribers. On the other end, it can test the, you can use the packet load to test the user plane. Okay, so we have two products. One is a emulator, which emulates tens of thousands of subscriber and multiple GNBs. Okay, which will load the 5G core network. Other one, we do have the real GNB where you can connect a multiple UEs, up to 1,000 UEs can be connected, and do all the real-time both voice quality and data testing using that one. So this is with respect to the testing the complete 5G network. So we do have a product where you can test a single or few of the network elements. At the same time, we can test the entire 5G core of the equipment manufacturers or service providers.
So this packet load 10G, this could load the core network with the high density of traffic, with the tens of thousands of UEs, and some real UEs here could be actually traffic as sending and receiving real traffic, data traffic, voice traffic, SMS, etc., and be transported across that same emulated network for testing end-to-end performance, correct?
Yes. So here packet load 10G is 10G is a name where it has a 10G interface, but it does have a lot of ports, so it can scale up to 40 or 80 gig per chassis.
Right. Okay.
So once the 5G core is tested, then you will be adding that IMS to do this VONR testing. So now you are putting the entire network, both 5G and IMS network, which can be tested for the voice functionality. So that is a very basic and important testing which need to be done. Make sure that voice and SMS are functioning properly. So GL has all the elements of IMS network as well, so it can be put together. And we have a ability to not only interconnect mobiles between the mobile technologies like 5G to 4G, 3G, 2G, but also we can connect to a traditional voice protocols like VoIP and SS7 and CAS network nodes.
Okay, so this is a very busy diagram. Voice over new radio testing requires an IMS. That's a fundamental requirement, whereas I think LTE does not require IMS, although IMS is very important for VoLTE, and that has pushed VoLTE. IMS has pushed VoLTE so that most calls these days, I think, are VoLTE, but 5G does require IMS to be present, so it will be another impetus towards for IMS development, as well as for this very high quality voice services. So GL has a 4G network, a real 4G network, very much similar to what Karthik was saying about the 5G network. And we can test deployment strategies and so on. But along with the 5G network, we also have the IMS core elements. All of these elements can be emulated by GL software or elements within the entire IMS cloud. So one of the important things that we'll show you in just a few minutes is the ability of the new voice over new radio requires that 5G phones register with the IMS. So we'll be showing you that. And in addition, what Karthik just said was this: we have these networks as well. We have IP networks and TDM networks and signaling gateways. So you can test the entire 5G suite of functions with our GL elements. Go ahead, Karthik.
Yeah, so this one not only, this particular thing will be used to various use cases. One is some of the educational institutes are interested in using this one to test and experiment. And GL provides scripting capabilities where individual network element functionality can be enhanced and modified. And also, this is used by so application developers where they want to emulate real 4G and 5G network impairments. So I think for them we are delivering these services.
Well, we've also had military and intelligence community purchase our products for their own purposes, for purposes of exploration and R&D development and so on. Our MAPS architecture is very relevant to those communities as well, because it provides an integrated environment for testing end-to-end, lots and lots of different protocols, as well as examining the protocols in detail. Okay, all right, so we're going to show you here, I'm going to turn it over to Rob. We're going to show you this end-to-end connection where we have real 5G phones. So I'll turn it over to Rob. Rob?
Okay, all right, thank you, DJ. So let's go back to this slide here. We would talk about this for a little bit, and I want to stay on here for a second. So what we have is we have 5G phones, real 5G phones. They're 5G standalone capable, so they support voice over NR, new radio. And in our lab, with this whole 5G network that Karthik has been discussing, we have a gNB, so a piece of hardware with an antenna that our phones will connect to, register, and be capable of making calls through our internal 5G network. So from one phone to another phone, we can make a call, and you know, that's great. We can make the call, we can hear a voice on it, and do all sorts of different things, and also take the phone and go out to different websites or do speed tests, things like that. So, well, we have in our arsenal, we have a voice quality solution. So what we're going to do, and I'm going to show you a short video of this, what we're going to do is take these two phones that are connected to our 5G network, and they're connected as over the AMR wideband. We're taking these phones and we're connecting into our VQuad solution, which includes our WTA HD hardware and our software, VQuad software, and these are connected through Bluetooth over wideband. And the WTA is going to not only control the phones as a Bluetooth headset, but also send and receive voice into the phone and coming out of the phone as a headset, so that we can make a call from this phone through our 5G network over to this phone, and then send voice into this phone, record it at this end, and do a voice quality analysis of it using the Polka algorithm, which is per ITU 863. And then we're going to send voice the other way and get a Polka result the other direction. And we'll also do a one-way delay measurement in both directions and some other audio metrics. So let me go through this. Let me show you the video. So again, this is the true network in our lab with two phones. You'll see the phones in the video as well, and how we supported this solution. So here's the video. So before I started, this is our VQuad software running on a PC in the lab. And I have two phones connected. This is phone 1 and phone 2. And I have a script that's going to place the call from phone 1 to phone 2, and then send voice for the VQT test and the one-way delay test. Let me run the video. Hopefully everybody can see this. So right now I am running the script. You can see the script going. Here are the two phones. Phone 1 is making a call. Phone 2 is receiving a call. And now the call is up. Let me pause this for a second. So now I have a call up on both between phone 1 and phone 2 going through our 5G network. Over here, you'll see that I have a connected state on phone 1 and phone 2. Prior to that, it would say placing call and answering call. So we now have a call up, and I'm going to confirm the call is up through the VQuad script, and then we're going to start sending and receiving voice. Let me continue the video. And so now we're transmitting and receiving voice, and it goes very fast. And here we have a one-way delay, okay, between phone 1 and phone 2. So now I'm going to do it the opposite direction, and I'll get a one-way delay in the opposite direction. So those are my one-way delay tests. Now I'm going to transmit and receive, but this is for voice quality. So transmitting from side 2 or phone 2 and recording on phone 1, and then analyzing, and then do it to the opposite direction from phone 1 to phone 2. And over here, this is actually the VQT software. So let me pause this for a second. So this is our VQT software, and what it's going to do is it's going to take the recorded file, which is a wideband file, going over the AMR wideband. It's going to analyze it against the reference file, the file that was sent, and it's going to give you a Polka mean opinion score, MOS. Now, the MOS is on a scale of 1 to 5, 4.13 being very good, especially for a mobile network. And not only are you looking at the VQT score, the Polka score, but you're also looking over here, the speech level and the noise level. So you can see there's very little noise between the reference and the degraded, and we've gotten the speech pretty much in line between the two. So there's no real gain, or the level's not higher or lower. So let me continue this, and we're just going to run a couple more tests here. During this, we're still in the same call, and here is another score, 4.15, and we'll run one more score. So it's running 2. These are female files that are going. You can send any file, actually, male, female, in most any language as well. So we just ran the 4 files, and we got the results of the 4 files. And now we're going to look at some other results that we can see here. So, for instance, I'll stop the video again. This is our P56 test, which shows speech activity, speech level, noise level, DC offset, RMS power. All this information will be passed by as part of the test for this same call. Then we'll also do an audio test. Now, this is my most important test, to be honest with you. This is the test I always look for. So it shows you the power level of the recorded audio, but more important, shows the bandwidth. Okay, so this is telling me, yes, we did sustain wideband. It's very important, because a lot of networks, when you're going through a network, you'll send wideband, you record wideband, but if anywhere in the network it doesn't sustain or it doesn't maintain AMR wideband, it's going to drop to narrowband, and it won't get back up, obviously. It'll stay at narrowband. So this tells me that our network was able to sustain AMR wideband, and the recorded file is a wideband file. And then last, we're going to do a audio dropout analysis. And here we're basically just looking at the recorded file against the reference file and determining if there was any dropped audio. And we're saying here that there was 0 milliseconds of dropped audio. So it's perfect audio going through our 5G network, which is very good. So that's basically the test of this. You see the call is now down, and the script will now rerun, placing the call. So when between phone 1 and phone 2, again, in our network. So over here on this side, you'll see placing, incoming, and over here you'll see that the call is now again connected. So that's basically the way we will run a test of voice quality and a delay measurement on 2 phones going through a network. In this case, it's going through our network. Again, it's going. We are going through our network from phone 1 to phone 2, going through the G node B all the way back. Okay. So one more thing I wanted to show. Actually wasn't planning on this, but I'm going to show it anyway. Let's see here. Okay. So we talked about data as well. And actually, this is another product of ours called GLNet Test that I installed on the phone. And I ran a quick test with it. I made a little video of this as well. and I'm running a TCP test on the phone going through our 5G network out into the internet. So I'm going out the 5G over the internet and getting results. So here it's a little blurry, but here you're seeing as a result of our TCP test, I'm getting a speed of 32 meg. This is a download speed, a delay of 2 milliseconds. So you're seeing a no retransmits, no basically no issues, no timeouts, and so forth. So it's a pretty clean test. And this shows that not only can we do voice and delay, we can also do data testing using the same VQuad solution. And this is actually just an app that sits on an Android phone, and you can run it manually. I ran it manually here, or you can run it automatically through the VQuad software. Okay.
Thank you, Karthik and Rob, for introducing it to 5G. So here I'll be talking about the 5G features testing solutions, what we can offer. So we simulate 5G network functions emulators. We can simulate all the functional elements in the 5G network. We can test each of the interface with the other one. So we can test GNB against AMF and AMF against GNB. So we will be assuming all the functionality of the UV within the GNB and all the other core elements within the AMF. So that we call it as a single interface. So where when we are talking about GNB and AMF, we will be just concentrating on the interface between the GNB and AMF. So that will be N1, N2. Similarly, we can simulate interfaces between AMF and SMF, that is N4, SMF and UDM, and UDM to AUSF or AMF to UDM. So all the nodes can be tested individually. So that we call it as a single interface testing. So another one is the 5G end lab, where we can emulate all the interfaces in the node, and can even emulate UVs, or we can connect real UVs for data and voice over new radio testing. And we also can have a 5G lab interworking with our other lab solutions for 2G, 3G, 4G, and IMS for the interworking calls. So we can call from 5G to 4G, or 4G to back to 5G, 5G to any IMS or VoIP phones, so or vice versa. So we can make calls and receive calls between any of the network labs we support. And we can simulate a massive number of UVs, and we can scale up to 64,000 UVs with the voice traffic. And we also can simulate user plane GTP traffic with a high rate ranging up to 40 Gbps. And the REST API simulations in the 5G core elements are supporting HTTPS and the TLS. So these are the basic major testing solutions we offer in 5G. Yeah, in these slides, we are just showing what interfaces we support, and each interfaces, what is the emulated node and what is the peer node, and what is the protocol simulated between those nodes. So this is just a list of the protocols which we support. So we have seen all these applications, or all these call flows, whatever you have seen. So these are the 5G testing solutions is simulated using our MAPS framework. So MAPS here stands for Message Automation and Protocol Simulation. This is a generic framework which is used to generate telecommunication protocol messages and transmission of the user traffic. So with this framework, we could emulate from all the protocols from legacy TDM networks to 2G, 3G, LTE, and IMS. The same framework is used across all the telecommunication technologies. So here MAPS is a built-in proprietary scripting language which is developed by us. All of the products which all of the MAPS products are come up with the ready-made scripts which make us the testing faster, and the scripts will be equipped to run a functional state machine of the node functionality. So this slide depicts the list out the common features of the maps application. So as stated earlier, the maps application is a script-based multi-protocol, multi-interface protocol emulation platform. So it gives unlimited ability to the customize any protocol messages or any fields within the protocol specification boundary. So if a user wants to corrupt any messages, so he has to insert the impairments. That capability is available. So the message level impairments can be applied to create invalid messages. Script is highly flexible. So in order to generate any of the desired protocol sequences, so user can create his own protocol sequences. So, and this application can be used for functional testing, performance testing, regression test, stress testing, etc. So all way of testing is possible with this map application. So this application is suitable for testing in every phase of the product development, as Karthik told earlier. So we can even use this application in the developmental phase or a testing phase or deployment phase. So this application can be used in all the phases. So maps can generate a different type of statistics and report generation. So, but it also provides user capability to customize the statistics and report generation to suit his requirements. And the application also can be integrated with other GL traffic generation tools to generate data and voice traffic. We can also integrate the application with the third-party automation. So using the Python based scripting, we expose high-level APIs for the Python scripting from the remote applications. Yeah, continuing with the maps features, this is the main GUI of the user interface of the application, which shows the call generation window. So maps comes up with a user-friendly user interface to generate and receive calls. So here you can see the call generation window, where you can see the script in the top pane which is running. And when you click on a script, you can see complete message sequence and the complete decode of the message in the right hand side in the real time. So we can display all the status of the calls, and we can log all the statistics of the messages which are sent or received. So these applications are also can be remotely accessed via another application. If you're running multiple nodes of with the maps application, so you can control by sitting at a single point using remote application. And the Python APIs will be exposed for automation testing.
So one thing you said that was very important, I thought, remotely access all servers from a single location.
Yes,
so as you saw, there were lots of elements in the 5G network, right? There's literally tens of elements, and all of those could be controlled remotely, right? Through just one remote application. By switching, you could start initiating all of them. You could initialize all of them. You can run certain scripts, automated scripts on all of them, and you can do this all remotely from a single location. Is that right?
That's correct, Vijay. We can.
Okay. Yeah, because the complexity of 5G is somewhat difficult to understand, because there's so many elements and they all interact. Once you have them all set up, you can go to all of them and then just initiate each and every one of those elements so that they start talking to each other and view, for example, the end-to-end transaction, for example, or do what Rob was doing, the end-to-end voice quality. Or you could even, create your own applications through the APIs. Okay, great, super. Continue, Bhavya.
Yeah, this is the slide which depicts the third-party integration, where we can expose the high-level APIs from the different nodes, AMF, SMF, or UDM, or AUSF, and all these functionalities can be controlled via Python application of Python scripting from any other system using maps CLI. Yeah, here we have capability to generate audio traffic over all kind of network. In this case, in 5G, here we are talking about the RTP voice generation. So on GTP traffic generation. So here we can scale up to 200,000 sustained calls.
Okay, so we handle all these endpoints. That's number one. So you saw Rob handle UEs, smartphones that are real off the market smartphones. They will connect directly to our network, our emulated network, or our real G node Bs, real E node Bs, real the 3G nodes, 2G nodes, etc. So they will connect directly to those, or IP VoIP phones will connect directly. There's a VoIP phone, and then or plain old analog POTS phones, and so on. All endpoints are supported, whether they're 4-wire or 2-wire, or whether they are smartphones or VoIP phones, whether it's video or headsets, whatever, any interfaces. And then all of these protocols will be supported. So you can have an entire network set up, and we have it in the lab. So you can generate traffic from legacy networks to current 5G networks. Okay, super.
Yeah, this slide shows the GTP traffic generation capabilities. So the GTP traffic uses another module. So where thousands of simulated clients can be simulated to generate to create GTP tunnels and generate the HTTP or playback the pre-captured HTTP files. And another gateway functionality we emulate, which will actually sends out the GTP packets generated by the clients to the web servers by removing the GTP headers, and whatever received from the web servers and encapsulates into GTP, and it delivers to the running clients. So we can simulate thousands of simulated clients and can verify the data. Yeah, we can play back only the pre-captured traffic files, text files. And another traffic generation tool is packet load. This is a data traffic generator, which is a 2U rack chassis. So here we can have either 4 1 Gbps NIC adapters or 4 10 Gbps NIC adapters, a total capacity up to 40 Gbps of a stateful TCP and HTTP traffic which can simulate. So this allows us to simulate massive UEs up to 500,000 with high density of mobile data traffic generation across UMTS, LTE, and 5G networks. So we can generate up to 40 Gbps of data. So the data generated will be encapsulated within the GTP headers and transmit through the gateways such as SGSN, GGSN, SGW, PGW, and in this case it is UPF. So simultaneous emulation of the multiple sessions can be possible, and we can also verify the bearer allocation bandwidth at endpoints. So the stateful TCP, HTTP, and PCAP replay traffic types are supported in packet load. So from this slide onwards, we will be discussing the 5G scenarios we support across each interface. So in this slide, we are showing the N1 N2 interfaces procedures. So here we can simulate UE registration, deregistration, identification, authentication, security, PDU session establishment, and UE initiated service request, context releases, and 5G MO SMS, data traffic emulation, VONR traffic. So we have just listed the main features. With these interfaces, we can act as GNB to test AMF or AMF to test GNB by just simulating N1, N2 and the user traffic. In this slide, we are seeing the N4 interface procedures, which include session establishment, session modification, session release, and data traffic emulation. So this interface is between SMF and UPF, and you can see the call flows which we have achieved within our MAPS application. So here session establishment, session and modification and deletion is shown along with the decodes. So here we are talking about the service-based interfaces. So in this slide, we are showing N8, N10, and N21 interfaces supported services. So here we are basically discussing the services offered by the UDM, so which include UE context management and subscriber data management. So in the screenshot, you can see the service requested by AMF, that is it is trying to register for 3GPP access for a UE with the IMSI ends with 1631. So it is registering for the UE to the UDM. So this is between the AMF UDM, SMF UDM, and SMSF and UDM. So all these nodes can contact UDM to retrieve the subscription data such as access mobility data, SMSF context, and SMS context information. Here basically we are saying showing N11 and N20 interfaces. This is between the AMF and the SMF. So basic services include PDU session establishment and modification and deleting. So this includes services from both AMF and SMF. So PDU session is offered by SMF and NEF communication is offered by AMF. So in NEF communication will transfer the NAS and the N1 messages to the SMF for the PDU session establishment. Here we are showing the N12 and the N13 interface. Basically, these interfaces for the authentication. N12 is between the AUSF and the AMF, and N13 is between the AUSF and the UDM. So whenever AMF requests for the authentication to the AUSF will contact UDM and gets the authentication vectors and calculates it and sends back to the AMF for the authentication, continue with the authentication. So the sample call flow is shown in the screenshot. Yeah, this is another new feature we have added. So this is event exposure. So we are allowing NEF to connect to our AMF or SMF to download the UE related to get the notifications of the UE event. So here we can subscribe. The NEF is subscribing to AMF for the events. So here it is requesting for registration event. So whenever the UE registers to this AMF, that AMF will generate a notification of the UE's status. So we are just showing a sample procedure here. Yeah, but we can expose many of the events such as registration, deregistration in case of AMF. In the SMF, we can expose PDU session creation, establishment, and release. I think now we have discussed all the nodes independently. So from next slide, I think we can just give you a glimpse of the end-to-end call generated using our application. So here we are showing the call flow between the GNB to the AMF, AMF to AUSF, EIR, and the UDM, and SMSF. So whenever the UE requests the registration, so AMF contacts AUSF for the authentication. Then AUSF contacts UDM to get the information of the UE, the authentication vectors. So then it calculates the authentication parameters and sends over AMF, and AMF will be contacting, sending that to the UE. So one UE responds with the authentication response, the same will be forwarded to AUSF. AUSF will confirm and notify the UDM. So once that is authentication is completed, security mode messages will be sent in order to encrypt the messages. So AMF then can contact EIR for the equipment check and UDM for registering for the UE context management, and it can download the NSSI information as well as different subscription information like access mobility, SMF selection, SMS subscription, etc. And once it downloads everything, it discovers the SMSF to be contacted, and it will instruct the SMSF to create the context, and then the registration will be successful. The PDU sessions will be created from AMF to SMF, and request will be sent, and SMF will contact UDM to get the session related information from the UDM, and PDU context will be created. Yeah, here we can see SMF is instructing UPF to create the sessions and modify the session. We can release the PDU sessions from the UE, so and send the deregistration. When the deregistration is requested, so all the information stored will be released or removed from the network elements.
Okay, thank you, Bhavya. All right. Well, thank you, everybody. We appreciate your attendance. And if you have any questions or you'd like to see an example or demonstration of our 5G implementations, products, we'd be happy to do that. Thank you.